I'm John Galt, for those of you who don't know me. I started this terrible journey here in digital imaging some 9 years ago when I joined Panavision and started the Advanced Digital Imaging Group. And prior to that, actually I worked for 10 years with digitizing film. So in this presentation, I'm not just going to be talking about digital cameras, but I think from the point of view of most of you here, we would like, you probably are well aware of film and film optical systems. And so what I'd like to do is combine both technologies so we can contextualize it, so you can see what's going on. And so I'm calling this Demystifying Digital Imaging Systems, because the same, it may seem from Larry's presentation that, you know, the imaging of digital cameras is extremely complex, but for 50 years, Panavision has used similar approaches, as have the other lens and film manufacturers. In fact, most of the information about MTF came from two great sources. RCA at the beginning of television with Autoshade and others, and of course Eastman Kodak. And the farther MTF measurement inside Eastman Kodak, although there were many researchers, but certainly a gentleman named Bob Lamberts, who actually left Kodak and started a company manufacturing MTF targets, which in fact, some of which we use. So basically, I'm going to repeat some of the things that Larry said. And I think that it's important that we realize that the picture element is important, but the number of pixels in the image have got to match all the other system components. As Larry alluded to, we actually concatenate the different aspects of the digital system. And I think that the most important thing to realize is that an imaging system is a system that starts actually with the scene, although we usually start to think about it with the lens. So it starts with lighting contrast. And you know, if you have low scene contrast, you know, go out and shoot a picture on a cloudy day, and you find it's hard to get a sharp-looking picture, and that really has a lot to do with the fact that the image contrast or the scene contrast is low, and it creates a low image contrast. So modulation transfer function is a mouthful, as Larry said, but it's what we live and die with. We do measure modulation transfer function in lenses and film and imagers, and I'm going to show you some practical devices for doing this. This is a kind of a repeat of what Larry was showing, and you can see on this, you know, in this case, black, gray, black, gray, black, gray target, that a graphical representation of that would be something like this: 0 to 100%, back to 0, and so on and so forth. In practice, as the frequencies go higher, that response, as Larry showed, gets less and less. A lot of people get confused with the idea of contrast, which is another word for sharpness, and limiting resolution. And a lot of that confusion started with this. Much of the need for very high resolution imaging started with aerial surveillance. And of course, the US Air Force target is extremely well known, and we use variants of that as a quick look to see whether or not a lens is resolving. Can we see 100 line pairs? Can we see 200 line pairs? And it's a very useful way of looking at an image. However, unfortunately, and the square wave is not a good, and that's what these little blocks basically represent. They're on-off. And they're not a good way of measuring a band-limited system, which is either an electronic camera or film that's digitized in a film scanner. So if we look at that individual bar, this would be a perfect representation. And as you can see, we've got a perfect representation of a square wave. I've never actually seen this anywhere at any frequency. This shows you 50% MTF, and you'll be surprised to know that 50% of the maximum MTF has a practical application in what you do. Because when you use depth of field tables, as I'll show you in a little bit, the 50% point, 50% of the maximum MTF is typically when we consider the image to be out of focus. And that's extremely important to know. As you can see here, you know, this is a very, very fuzzy image, but we're still measuring 5% MTF. Now, the reason for that Air Force chart is that a trained observer, and typically they're actually looking at stereograms, but a trained observer without any electronic manipulation whatsoever can easily see 0.5%. So if you're trying to find Osama bin Laden in the desert somewhere underneath a camouflage tent, that 0.5% becomes really critical. And there are image processing techniques that actually allow you to extract information at even lower modulation than that. But for motion picture applications, it's completely useless. Now, I mentioned a sign pattern. This is actually a commercial pattern made by Sign Patterns in Rochester, the company founded by Bob Lamberts. I'm sure they appreciate the commercial. We're about to look at this row of frequencies. Now, they are actually, you can see, somebody once said to me, how can you make create a measurement with a fuzzy image? And you can see this at the low frequencies. You see there are no sharp edges. What you have to imagine is that you're actually looking down on a sine wave. This is like looking down on the peak. And this kind of measurement results or this kind of image rather results in a waveform pattern that looks like this. And so this going from low frequencies on the right-hand side to high frequencies on the left-hand side is the kind of image that you would get if you pointed a camera at the sine pattern and used the line function to isolate that line. It's kind of impractical, I feel, because when you line it up and you fill the screen, then you have the high frequencies at the edge of the frame and the mid frequencies in the middle and the low frequencies at the other edge. We actually devised our own pattern, and this one is slightly different. This is courtesy of James Pearman here. And what he has done, and you're seeing aliases, by the way, beautifully that Larry referred to, when we take these higher frequencies that are beating with the raster of this presentation and the projector. So, but what we've done here is we've groups of frequencies, and you see the highest frequencies in the middle. It doesn't look it because you're seeing an alias. But that is imaged, and I don't know whether you can see this, but down here it shows you how you're supposed to image it. You put this whole target in a third of your field. Now, you can move it around, of course, if you want to see what the edge resolution was, but essentially you simply image this target, and the real target's about 11 by 14 inches. In a computer, we can actually then get the average, if you like, of the response of each of these frequencies and draw a curve. There's another way of measuring MTF. This is the Panavision MTF bench. The principle is extremely well known. Here we have a lens under test. We have a target, which is a slit. It's just a vertical slit rather than having a whole bunch of frequencies. And a light source shines through that slit. And back here we have a line array CCD camera. And this is a close-up of the slit. At least I think it is. Here we go. And so that's what the lens is looking at, and is through and is imaged onto a line array CCD. Now, if you remove that, that would be an ideal representation, an impulse response of that slit target. In reality, we end up with a spread function that looks something like this. And that line spread function, through a mathematical transformation that happens in that computer back there, will give you an MTF curve. Now I'm going to talk a little bit about film imaging systems. Professor Bill Gland at Florida Atlantic University Imaging Lab always used to say to me, everybody thinks resolution is 2 to 4 times greater than it really is. And a lot of that has to do with confusing contrast and limiting resolution. But this is what really happens in a film imaging system, and I'm going to show you some actual measured examples of this. You take the MTF of the lens and you multiply it with the negative. The negative, the film itself, and Kodak publishes this, by the way. If you get onto their website, they'll tell you what the MTF of their different film emulsions are. In fact, they'll give you the MTF for the different layers in the emulsion. And an interesting thing, when you get to the higher spatial frequencies, you'll discover that the yellow or blue sensitive layer has got twice the MTF of the cyan or the red sensitive layer, and that's because the light that hits the cyan layer has to travel through the emulsion. The photons ping pong off the silver halides, in fact, go right through the cyan layer, hit the antioxidation backing, and come back into the cyan layer. And the green, which is where most of the eye sees contrast, is in the middle of that sandwich. So then we make an IP from the negative, then an IN, then a print, then the projection lens, and of course I forgot the eyeball, the viewer. So, but what you can see is that we have 1, 2, 3, 4, 5, 6 cascaded functions. So even if each of those was 90%, and by the way, only at very low frequencies is that true. We, Panavision, typically measure different frequencies, but the number that is most important to us is actually 20 or 21 cycles per millimeter. And if you multiply that out across a 24 millimeter wide piece of film, i.e. Super 35 without a soundtrack, you'll find that that's only 1,000 pixels. So that is where we want to see 80 to 90% MTF in a lens. The negative, as you'll see, has a rather strange convolution because it's nonlinear, but the final system, if you multiply all of these out, 90 times 90 times 90 times 90, you'll end up with 53. Most important is if any one parameter is 60%, then the final system MTF will only be 35%. And that is extremely important for photographers because it doesn't matter how many pixels you have, it doesn't matter what the lens is, it doesn't matter how good, I mean, you've all seen wonderful images destroyed by a bad projection system. And all it takes is one of these 6 elements to be only 60% and your final MTF is 35. And that 35 is really important, as you'll see in a moment. So this is that system I just showed you. And the important thing to realize is, I'm just using, obviously, our lenses that we've measured. These films are not that important. This is the 5244 is the intermediate film at the time when I made these measurements, and 5277 I think is still an emulsion in use. But you do it with the latest emulsion, and you don't get much difference in performance. And the important thing to see is you see they're all very, very well matched. I mean, these are their individual contributions. These little bumps are caused by chemical sharpness and nonlinear transfer characteristics of the film emulsion. I know you're used to hearing about, image enhancement is evil in an electronic camera, but since the late 80s, Kodak and Fujinon have been using these things called development inhibiting release couplers, which adds chemical enhancement and drives visual effects people nuts, right? Because it creates an artificial edge, and that's what you're seeing here, this little belly that goes up above 100%. But as you can see, they are all quite similar. You can see how well the Primo matches. You can see how well all of these lenses match. But yet, the final MTF, as you can see, is considerably reduced. And down in the bottom here, what we're looking at is so-called 4K, which is 80 cycles per millimeter on a Super 35 frame. In other words, a frame that would be 24 millimeters across. And you can see that the final MTF, and this is, by the way, is not, you know, a print system. This is a DI system. The final MTF that you'd get in the screen is, well, actually, this is before the screen because there's a couple of other stages. We now need to scan that out and project it. So where we measure lenses, by the way, is around here, 20 cycles per millimeter. As you can see, that's only 1,000 pixels across the frame. But what we're looking for is we're looking for this 90% MTF at low spatial frequencies, which coincides with the human visual system and our perception of sharpness. Here, this is, Larry showed you, I believe, part of this curve. And these little bumps here are the aliases that we have to remove. And you can see that, you know, if you go to a higher resolution system, and this would be represent the MTF of a 4K sensor, you know, there are advantages to doing this. This would have its own alias if we continued on. One of the major advantages would be you could do a much simpler filter and retain the lower frequencies. So the concept of supersampling is one which we, as the technology improves, we will be doing more and more of. Instead of having an absolute relationship between the number of pixels or photosites, I'm sorry, I can't even correct myself from that, the number of photosites and the final representation of the image, ideally we want to supersample the same way we do in audio. Now, I'm going to talk about depth of field, which seems like a strange thing to be talking about when we're talking about resolution, but depth of field is a very interesting construct. Although we use formulas, the formula is an empirical formula based on people's visual examination of images. And what the concept is that if I can focus on a point source, ideally, which is in the object space, ideally I should be able to create a point in the image space. And even a very, very good lens can do that. In fact, that's the whole basis of the MTF measurement. However, what we've determined over the years is that the amount of defocus, the so-called circle of confusion that's allowable, will tell us when an image will be acceptably appear to be in focus, even though it's out of focus. Because there's only one plane of focus, but this point in front of the plane of focus and this point behind the plane of focus will be acceptably sharp. And depending on what circle of confusion you choose, your depth of field will get less. And this is one of the big problems about the idea of going to a 4K system. If it was truly 4K, by the way, and not just marketing pixel numbers, you would really have, you know, 4096 red, 4096 green, 4096 blue, and there have been some experimental cameras built like that, and their images, the image is basically similar to what you would see with an IMAX print. So this is the thing I wanted to show you. When we measure, and this happens to be well, that's a serial number too. This is a Primo, 150 millimeter Primo at T2.8. And the three colors, you have 25 cycles per millimeter, which is the low frequency. It's a little bit higher than what we normally make our measurements at, but quite similar. 37 and a half cycles and 50 cycles. And here's the contrast at the depth of field limit. So, in other words, we focused at 8 feet, and our depth of field is from 7'11" or 95 inches to 8 foot 1 or 97 inches. Remember that 35%? As you can see, at 25 cycles per millimeter, the MTF is dropped below on the near side and is more or less at the 35% on the far side. So this is really what we consider to be the absolute limit, the lowest MTF that will still give you a sharp image. Now this is it's a contextual thing. If you see the image on its own, it might look quite sharp, but you know, if when you look at an image, you see things that are sharp and things that are not sharp. In fact, if everything's sharp, everything looks unsharp because there's no depth and there's no sense of sharpness. In fact, remember in that equation a few minutes ago, I said if a 60% input is input into that MTF equation, the result would end up being out of focus. Now, this is the sharpest lens that I have. I use it for a lot of measurements. Not a lot of people like to use it because it's a big, heavy lens. But it, as you can see, has at 4K has excellent MTF, 60%. But at 80 cycles per millimeter, which is 4K, but that lens fed into our MTF equation would still result in an image that would have that would appear to be unsharp. At that resolution, at lower resolutions, at 2K, it will look wonderful. However, this is a printing Nikkor, which is, and I'm not picking on Nikkor, they're the most popular optical printing lenses used, and they're used in all kinds of film scanners and all kinds of optical systems. But you can see that, I mean, this printing Nikkor, I believe you can buy for about $4,000, and this 125 millimeter Primo, I don't know what the most recent build cost is, but I imagine it's somewhere close to $20,000, and that's what it costs to build it. So, you know, but the point here is that if you were going to scan film, let's say with this lens, and you were scanning at 4K, you know, it may make you feel good, but you're not really going to get anything out of it. These were high-resolution images. Obviously, for the projector, we're only using a part of the image, but I wanted to show you practically what this means. So this is now when it says maximum MTF on this particular lens, this is 2/3 inch, and I believe the MTF was actually about 75% at 50 cycles per millimeter, which is one of the issues we'll get back to in a bit, because the smaller the sensor, the higher the frequency response necessary, which is kind of at odds with what the camera manufacturers are doing, because they keep using smaller and smaller sensors and then saying to Canon and, you know, make a lens for this. And of course, you know, the electronics guys love it because it makes the sensors cheaper, because the yield on a CCD varies as a square of the area on the wafer, but it's simply, you know, impossible to get high contrast in these little tiny handycam type cameras. So this is 50% MTF. So this would be considered to be the limit of your depth of field. Now, it's 50% of maximum, which typically is somewhere between 35 and 40. And that's a close-up of 50%. So on its own, it would still, you know, you're still resolving fine detail. I can still see individual hairs. Back to our early images where we showed the 5% MTF. And there you can see the 5% MTF, which, if you were looking at a high contrast target, you could go up to the screen and say, yeah, I can see that, or even less. But from a motion picture imaging system, 5% is very, very, very out of focus. Let's just run through it very quickly. So that was what, you know, that's graphically what we're looking at, back to that original chart. And I'm going to, with that, I'm going to hand it back to Larry.